As we start to get more quantitative about how we think about the electric force, I'm going to want to introduce a concept called the electric field. But I think it'll be profitable to spend a moment and just talk about fields in general. So, to a physicist, and the mathematical definition of a field is slightly different, but to a physicist, the way to think about a field is as a representation of any physically measurable quantity that can vary in space. And there are many kinds of fields. I'll just give a couple quick examples of what I mean by this. So, for instance, let's think about a scalar field. What I'm talking about here is that at every location in space, I have associated a scalar variable. An example of this would actually be if you look at weather forecasts and you look at a temperature map. So, pardon me while I draw a really lousy state of Michigan. There we go. Lower Peninsula, Upper Peninsula. Yeah, sure. Anyway, the point is you can go and if you go and look at temperature maps, what you'll see them do usually is they'll draw these bands across the state, like so. And they'll say, within this band, the temperature is about this. And we can take this a little further. If you were super detailed about it, we could say, look, right here in the state of Michigan, and find out that at this location in the state, let's go ahead and say it's a nice spring day or something like that. Might be 19 degrees Celsius there. Go up a little further north, say right here, something like that. It'll be a little cooler. Maybe it'll be 14 degrees Celsius or something like that. But the point is that for every single location in the space, for every latitude longitude pair, we can associate, in this case, a temperature. So this would be an example of a scalar field. Similarly, an example of a vector field following the same weather idea would be a wind map. Now, the way actual wind maps actually get printed, there's a funny way that they're done for historic reasons. So this would be more of a physicist wind map, something looks something like, I don't know, this. Oh, I can't stand that. Okay, that's gonna have to do. But the point is that if you look at wind maps in a weather forecasting app or something like that, again, we'll say at some particular location in the state, the wind is recorded to be going this fast in this direction, and then maybe somewhere else it's going slower and in a different direction, and maybe right here it's actually fairly calm, and then right here where there happens to be an archery tournament or something, of course, that's when you get the massive crosswind. Just my luck. All right. Well, anyway, so the idea here with a scalar field, like a temperature, think like a temperature map. I input a latitude and longitude, out pops a scalar value, in this case a temperature. I can do the same kind of idea. I can pop in a latitude and longitude and say at this location I have a magnitude and a direction, or I could do X and Y components if that floated my boat more. But in this case, we can be saying the wind is blowing this hard and in this direction. All right. Now, it turns out that we can also do this for forces. And to this point, I need to introduce one of the big discoveries of the early 20th century as we work our way towards the electric field. And that is that space, there we go. Space is a thing. Now, what is an open research question is, what is the thing? Nature gives up her secrets very slowly, but we found out that space can be deformed. And if it can be deformed, that means that in some sense or other, it's a thing. And it turns out that this thing has properties. So, as we'll work towards in a moment, let's just say we're thinking of two electric charges, Q1, Q2, like that. Now, what we have come to understand is that the interaction is not directly between the two electric charges, even though we do see that Newton's third law, the force of on charge 1, force on 1 by charge 2, and the force on charge 2 by force 1 are indeed a third law pair. They're equal and opposite. We find that the, at least in as long, are equal and opposite, at least as long as things aren't moving too crazy fast. And even then, it still respects Newton's third law. It's just more complicated and beyond the scope of this treatment. But what we found happens is that this charge here, when it doesn't directly interact with this. Instead, this charge somehow modifies space. And then the idea is that space will interact with the other charge. And, as Newton's third law would have us expect, this goes the other way. This charge as well, my Q2 charge here, modifies space, and then space interacts with this charge. So it's not a direct interaction between Q1 and Q2, but instead space is somehow the middleman. Space somehow gets the memo, is how I like to put it. Space somehow gets the memo that the charge Q1 is located here. This modifies a property of space that we will call the electric field. And then at this location, space, the electric field property of space will interact with this charge Q2 over here for us to feel the force on charge 2 by charge 1. And vice versa. The space also is getting the memo that this charge exists that somehow is modifying the electric field property of space over here. And then this electric field property of space interacts with this charge. So charge modifies space, space interacts. Charge modifies space, space interacts. And Newton's third law is always respected, although things can get a little wonky if things are moving real fast. But even then, Newton's third law is still respected. It's just that the math can get ugly. Anyway, as a segue, or as a scaffolding point, I think, before we dive straight into creating the electric field, I think it's maybe profitable for us to spend a moment and visit for the first time, kind of, the gravitational field. Now, I've been mentioning that lowercase g is what's called the gravitational field strength in my previous series of videos. Here we'll finally get to do this treatment properly. Now, that being said, I do have to put in a bit of a disclaimer. It turns out that the exact rules of what's going on with the gravitational field are unique compared to the other forces of nature, and it adds some complication that won't help with this discussion at all. So everything that I'm about to say is true in what's called the weak field limit, which is basically we're pinky swearing that we will not stand too close to a neutron star or a black hole. So as long as we just deal with normal planet-sized objects, we'll be just fine. But or even reasonable stars, but neutron stars, black holes, other weird things like that. It turns out that there's more going on under the hood than what I'm presenting here. So I just want you to be aware of that. Anyway, let's just imagine that we've got the sun hanging out here. There we go. And now what we can imagine is, say, what if I place a rock of mass m, let's say, right here? Well, we know that it will feel a gravitational attraction towards the sun. And similarly, if I were to put a rock out here, it would also feel a gravitational attraction to the sun. And if this were the same rock that I moved from here to here, the gravitational strength would be weaker. That's why I drew a shorter arrow. All right. So the strength of the interaction is given by Newton's law of universal gravitation, which says that the strength is G, big G, which is the gravitational field strength constant, the 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That one, not the 9.8 number that you might know. M over R squared, where R is the center-on-center distance from the sun, or whatever object, to the other object we care about. Now, we could, if we wanted to, although in practice, since gravity always attracts, unless you're launching satellites to travel through the solar system or something like that, the need isn't that strong. But what we can do to at least more correctly represent what's happening physically here is we can define what's called the local gravitational field vector. Lowercase g, yeah, that g, and is a vector. And we can define it to be the gravitational strength that, say, the sun or whatever would apply on some, what we'll call a test mass. This is just physics jargon. The idea is that this is some small mass, and you might ask how small is small. Small enough that we don't have to worry about it tugging on this mass here, tugging on the sun to anything that's going to matter for our calculations. It can be vanishingly, infinitesimally small. In a certain sense, this is the physicist's fancy way of making up a number. But the thing is that this test mass only exists in our mind. It doesn't have any physical reality. But what we can do is we can imagine, say at this location, instead of sticking a real rock here, I could stick my test mass. Maybe it's like 1 picogram of mass, whatever. Just, some small, small enough amount of mass. Even on scale of the sun, this could be a decent little asteroid or something like that. And we can say, okay, if I put it there, it's going to exert a certain amount of force. Now, what I'm going to do is say that this gravitational field strength is the gravitational force that test mass feels with the test mass divided back out. Now, how am I going to interpret that? Give me a moment. First, let's just go ahead and figure out what it is in the case of the sun. So if I go and stick a test mass in here, the strength of the interaction would be G times the mass of the sun times my hypothetical test mass over r squared. And I'm going to take the whole thing and divide it by my test mass. And since this is a vector, we have to include the direction. So this is towards, in this case, the sun, or just towards big M. Okay. So the big deal here with the test mass is that it'll cancel out, which it should, because it only ever existed in our mind. And we get that the gravitational field strength anywhere due to some point mass will be gm over r squared, and it'll be in the direction of being towards the mass that created the field, as we say. So what's this mean here? Well, the idea is that I could, if I wanted to, go ahead and I'll just redraw the sun here. So I could, if I wanted to, I could do this exercise literally everywhere. And I would get, say, at this location, my lowercase g will be a reasonably large value pointed towards the center of the sun. And then at any same distance, I will have the same magnitude, but the direction will always be towards the sun. Like that. And if I'm farther out, like say over here, the gravitational field strength at this location will be towards the sun, but it'll be weaker. That's what I'm showing with the shorter vector arrows. Something like that. All right. Now, the whole point of this exercise, the way we can think about the gravitational field strength, is it is telling me the space got the memo that the sun is here. And it modified what we call the gravitational field strength property of space. And again, this is an approximation, what's called the weak field limit, but that's fine for what we're doing here. And what this is telling me is if I were to go and actually put a rock here or something like this, so not a test mass, but now I'm imagining putting a real mass in here. The force that real mass that I would put at that location would be the mass I put at that location times the gravitational field strength at that location. So this seems like a really long roundabout way to write Newton's law of universal gravitation. We calculate all but part of it to get this gm over r squared business, and then we times by the little mass over here, and it doesn't seem like it provides us with all that much. And to be honest, for gravity, unless you're doing something complicated like launching satellites or something like that, you know, through a planetary system, yeah, it's not much utility, but at least conceptually it makes it clear to us. The sun the space right here somehow got the memo that the sun is right here. The sun being here somehow modified a property of space right here. This property of space we call the gravitational field strength at this location. It is a vector associated with this location. So there's nothing going this way or anything like that. Just at this point, we have associated a vector. Just like with the winds map that I showed you, at a particular location, the wind speed and direction is something, but you could move a meter over and it'll be something different. Maybe not by much, but it'll be different. Same kind of deal here. This is telling us how hard gravity would pull per unit mass of stuff I put here and the direction in which it would pull. All right, so let's just go and take a look at this in the case of the Earth. So say you're near the surface of the Earth. So there it is, Earth. Now let's say I'm going to put my eventual goal here is I'm going to put a real mass M right here. Now, the deal here is that what's going to count is this distance from the center of the Earth to my mass. But the point is that is near, if we're close enough to the surface of the Earth, that is so not going to matter compared to the radius of the Earth. So what we can do is we can calculate the gravitational field strength at this location here. It'll be G times the mass of, big G, times the mass of the Earth over R squared. But the point is, if I'm near the surface of the Earth, the radius of the Earth is 6.37 million meters. If you're talking about a person standing on the surface of the Earth, their center of mass is like a whole meter higher than that. We are so not going to get strung out about less than a part per million difference in radius. So we can say that the gravitational field strength is G times the mass of the Earth over the radius of the Earth squared, to an excellent approximation on the surface of the Earth. Let's go ahead and put in the numbers. G, big G, is the universal gravitational constant. It is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.972 times 10 to the 24 kilograms. And the radius of the Earth is 6.371 times 10 to the 6 meters, and we'll square that. Now, if you grind all those numbers through your calculator, you'll get 9.8. Now, let's figure out the units. Let's see. We lose 1 power of kilograms here. This meter gets squared, so that's going to cancel both of those. I'm left with newtons per kilogram. Now, dimensionally, Newton per kilogram has the same physical dimension as meters per second squared. And a lot of books will actually write it that way in an attempt to not confuse you, but in my way of thinking, it does end up confusing folks. So we can go ahead and say, revisit free fall real quick, just to see how this is going to work out. So remember, in free fall, that the physicist's definition of free fall is gravity is the only force acting. Okay, so now by Newton's second law, the acceleration will be the net force over the mass. Now that force is gravity, because it's the one only force, and that'll be over the mass. Now, an important note here, and this was in my previous series of videos, this mass is what we call the inertial mass. This is telling us how hard it is to change the velocity of a thing. But now, if we go ahead and plug in here, this will be mg over m. This mass here is what we call the gravitational mass. And what we know is that experimentally, even though mass plays, which tells us how hard gravity is pulling on something. Now, we know these are two different functions, but we know from very careful experiment to at least on the part per trillion level, if not a bit better, these two values are the same. And so physicists just assume they are the same, which is why we don't write an m sub I and an m sub g to keep them straight or something like that. We just get the m's canceling. All right, well, we probably should check, are the units going to balance here? So over here, this is meters per second squared. And then over here, I have newtons per kilogram. Well, a newton per kilogram, a newton is a kilogram meter per second squared. And then if I divide by kilograms, sure enough, the units check. And I will get that my acceleration is 9.8 meters per second squared towards the center of the Earth in this case. And if you're on the surface of the Earth, you're just going to call that down. I bring up this distinction between inertial and gravitational mass, not that we're going to care about it here, but to draw a bit of a distinction between what's happening with gravity and why, honestly, we don't get too strung out about doing a field treatment of gravity unless it becomes technically very necessary versus doing it for the electric force. And the reason here is that because of the electric force, this M is not going to be an M anymore. It's going to be a Q for the electric charge, and then there won't be a cancellation. And so that's how the electric force is going to be different than gravity. All right, so let's go ahead and follow that thought out here. So the electric field will be defined in the same kind of way that we just defined gravitational field strength. The letter is E, and you would think, oh geez, that's annoying. Why is it the same as you have for energy? Yeah, I'm sorry. The only thing that can help here is that E for energy is a scalar. This is a vector. Yeah, sorry, try to keep them straight. A lot of this you can blame on James Clerk Maxwell, the person who demonstrated that the electric and magnetic forces were two aspects of the same thing. When he developed his theory of electricity and magnetism, he basically just worked his way down the alphabet, coming up with variables. So there's an A, there's a B. B will be the magnetic field. There's a C, the speed of light. There's a D, which we won't see in this treatment. And we won't see the A either. There's an E. There's an F. You get the idea. He just worked his way down the alphabet, and I would like to think that he matched the E for electric field, but with B matched to magnetic field. Yeah, I think he just worked his way through the alphabet as he needed it. Anyway, the electric field, which is going to be a function of our location of space. So I'm just going to write X, Y, Z, just for us to be very clear. I put in coordinates, and I will define it in the same kind of sense here, which is that it'll be some force on a test charge. So instead of a test mass, it's a test charge. Some vanishingly small amount of charge. X, Y, Z. With that test charge divided back out. And the units of this are going to be newtons per coulomb. So just like the gravitational field strength was newtons per kilogram, this is newtons per coulomb. Now the difference is that this isn't going to be dimensionally the same thing as meters per second squared. It's just its own thing. Okay. So again, it's going to be the same kind of deal. If I know the electric field at some location, oops, usually people like to draw these in red. If I know the electric field at some location. So again, this is purely a vector value that we have associated with this location in space. I can pick a different location and that electric field vector will be a different length and a different direction. What this is telling me is if I were to go and say put a positive charge at this location here, I would be saying, okay, the electric force that we would be feeling is QE. And a positive, if this is a positive charge, a positive number times a vector is another vector that points in the same direction. So if I were to put an actual physical positive charge at that location, it would feel an electric force parallel to the electric field at this location. On the other hand, let's say I go and stick a negative charge there. Again, the beauty of this is we can still say the electric force is Q times E, but now because Q would be a negative number, the electric force will point in the opposite direction, anti-parallel. So this is particularly handy for us here. So here, since this Q was a negative number, we end up having the electric force anti-parallel to the electric field. So in a certain sense, it helps to make the bookkeeping a lot easier. We can calculate an electric field and then worry about which way a charge will feel a force until such point as we actually put the charge there. But it's still telling me at this location, for every coulomb of charge I put there, I will get so many newtons of force out. An analogy that I like to think of is it's kind of like the price of bananas. You go to pretty much any store. There are a handful of stores that do sell bananas by the banana, but most places sell bananas by the pound or by the kilo, right? And so there'll just be a sign up, so many dollars per pound. And what that's telling you is, okay, or so many cents a pound. And what that's telling you is, okay, if I buy 1 pound, that's how much I would pay for the bananas. If I buy 2 pounds, I would buy twice that amount. If I buy half a pound, I'd pay half of that amount. So it's telling me how much money is going to come out of my wallet per pound of banana I buy. But the actual amount of money that comes out will also be dictated by the amount of bananas I buy. It's the same kind of deal here. There's no forces being exerted or anything like that at all until I put a charge here. And then this property of space right here, the electric field, which is due to some other charge or collection of charges somewhere else, the electric field at the property of space at this point right here that we call the electric field, space is going to interact with this electric charge to give us this electric force. It'll be parallel if I put a positive charge there, negative if I put or anti-parallel if I put a negative charge there. So that helps to make the bookkeeping a lot easier. Because otherwise, let's say, if we think back to the force map that I first did with the sun and gravity, if I did something similar, say for a point charge, let's just say I put a positive charge Q right here. First off, I would have to be keeping track of if I were to place a different charge. We'll just say it's a test charge. I would have to first say maybe draw everything in blue to say, okay, if I put a charge there, it will repel, but not that strongly. If I'm a little closer here, it'll repel, but a little more strongly. If I put it right here, it'll repel very strongly. But then I would have to like go and draw all this again for the case of what if it's negative. And I say, okay, I get a weak attraction here if it's negative, and I get a stronger attraction here if it's closer by, and then I get a really strong one here. And you can start to see that this gets cluttered. Like this arrow is going right over the charge. You could have the arrows start to cross each other. It's a mess. So one of the nice things is we can just plain draw an electric field map instead. So I would draw that same, what we call source charge. And then I just draw my vectors like so. There we go. Something like that. And that tells me everything I need to know, because since I drew the electric field, I already know if I place a positive charge at that location, it'll feel an electric force in the same direction. And if I place a negative charge there, it will feel one in the opposite direction. All right, so let's wind this down by finding the electric field due to a point charge. Then the idea is pretty much everything else can be assembled up from this. So the idea here again, let's just, for the sake of clarity, this is what we'll call my source charge. So this is the charge that the whole rest of space is going to have to get the memo that this charge exists. And just for simplicity's sake, we'll say that this charge is positive. All right. Now my first step is going to be to imagine placing test charges in different locations and seeing what we get. So if I put a test charge here, it would be like that. It would feel an electric force like that. It would feel an electric force like that. It would feel an electric force like that. Now, the point for all of these is that by Coulomb's law, the electric force on our test charge will be K, Q, our source charge, times my test charge over R squared. And then this would be away from Q if positive, and then similarly we could argue that it'll be towards Q if negative. And then to get the electric field at that same location, I just divide the test charge out. So since I gave a verbal description of the direction, I can write that as a vector there. The electric field will be the electric force with the test charge on our hypothetical test charge, which again only exists in our mind, except it does tell us what will happen to a real physical charge if I do happen to put it there later. This will be K QQ test over R squared, and then I divide out the Q test. So the test charges cancel out as they always must. To end up with 1 over, KQ over R squared. This K also often gets written in terms of a different quantity called epsilon naught. When it does, that gets written as 1 over 4 pi epsilon naught Q over R squared. And again, it's the same deal as far as the direction goes. So I'm just going to copy paste the directions I was writing on my test charge. And, oops, put them right there. So my electric field strength goes as the source charge over R squared, and it'll be, in the direction of it will be away from the source charge if the source charge is positive, towards it if it's negative. Then later, if I actually want to find an electric force, I just can go ahead and say the electric force on some charge Q will be equal to Q times the electric field at that same location. And so this gets back to what I was saying before. First off, this kind of formalism helps to make clear that what's happening is that the charge modified space interacted with the charge. The second thing, though, and where this comes in more convenient than it does for the similar construction for gravity, is that you don't have to keep saying, oh, but it'll be the opposite if the charge is opposite. That all gets baked into the cake. And so it allows us to talk about electric forces in a way that is more independent of the charge that's on the receiving end of our attentions.